Modern systems analysis relies on tracking multiple temporal data streams simultaneously. But as we monitor more channels, we quickly hit a limit on what the human eye can process at once. This signal graph maps 3 continuous channels over 10 seconds. While effective for single metrics, plotting 3 variables degrades clarity. Between seconds 2 and 4, overlapping lines obscure the exact state. You cannot distinguish baselines from critical spikes when data occupies the same space. Attempting to resolve this with textual annotations or event markers only increases the noise. An effective visual system must track the timeline, map the fluctuations in intensity, and isolate specific event triggers, all without allowing the data paths to cross. As dimensionality increases, traditional signal graphs reach a limit where the data is no longer readable. Researcher Umair Abbas developed a structural solution to this clutter, the Chromatic Data Sequence Matrix, or CDSM. This vertical strip of 3-column circular nodes functions as a structural algorithm for time series analysis. It encodes precise quantitative data into visual states, creating a readable rhythm of information. The CDSM integrates the functions of a chronological timeline, the amplitude of a signal graph, and the density logic of a heat map. The result is a compression of continuous temporal fluctuations and isolated event metadata into a single vertical sequence. To understand this matrix, we must isolate its fundamental unit, the data node. Each node contains 3 properties. First, its y-axis position acts as a timestamp. Second, fill color dictates intensity. Purple is 1, blue 2, green 3, and red a peak of 4. Third, the outline is an event override. A red ring flags an anomaly or a threshold breach, while a neon green ring confirms an optimization point. This design embeds annotation directly into the signal, removing the need for external labels. A single chromatic node carries 3 dimensions of data, time, amplitude, and metadata, simultaneously. We can demonstrate the mathematical rigor of this system by translating a controlled 10-second data slice. We'll use a 3-panel framework to look at 3 representations of the same data. The left panel is the CDSM format, tracking from second 0 to 9. The center maps color intensity into a waveform. The right converts outlines into a narrative log. All 3 panels share exact horizontal alignment based on the vertical time mapping. This alignment proves the matrix contains the same empirical payload as standard analytical tools. To see how these layers interact, let's look at second 7. At this timestamp, the matrix shows 2 red-filled nodes and a green node with a green ring. This visual cluster translates to a mathematical peak of 3.67 on the signal graph and a critical event marker on the timeline. Now, compare this to second 6. Here, the nodes are primarily purple. This corresponds to the lowest amplitude trough on the graph and a dormant phase on our timeline. Finally, at second 1, we can see how metadata overrides the state. The nodes are blue, indicating a baseline state, but the neon green ring translates to a reinforced stability marker without changing the numerical amplitude. By collapsing amplitude, event flags, and time, the CDSM provides a unified reading that a separate signal graph cannot provide. This is the 60-second matrix sequence. It utilizes Gestalt psychology, where the brain groups elements to perceive structure first. Clusters of blue and purple instinctively read as stable operational plateaus. By processing these groups as a vertical sequence, we recognize states before reading numbers. Rapid shifts in color reveal system transitions and volatility at a glance. Evenly spaced green rings show a stable periodic trigger, while isolated red rings expose unpredictable stochastic events. This rhythmic interpretation allows an analyst to perceive system health instantly, reducing the cognitive time required to find an anomaly. Most industry dashboards force users to cross-reference multiple disjointed panels. The CDSM collapses that data into a single architecture. The system matches the rigor of established models while delivering the information through a more efficient visual structure. It demonstrates that minimal geometric variation and color modulation are sufficient to carry a dense mathematical payload. As data dimensionality increases, we require visualization tools that scale without increasing the cognitive load on the analyst. Internalizing the logic of these nodes allows for the direct reading of a complex dataset.
The Chromatic Data Sequence Matrix unifies the timeline, the heat map, and the signal graph into a single visual language.